Hi guys, this is Mrs. Hammer. Welcome to this video about balancing chemical equations. If you're at Richardson High School and you're following along in your notes, this is probably pages 1 through 3 of your notes. If you're not at Richardson, this is probably still just a useful practice video to help you learn how to balance chemical equations. Thanks for watching. Let's get into the notes.
Alright, so we're going to get started. Again, our goal by the end of this is that we should be able to write a balanced chemical equation. Basically, we have to obey the law of conservation of mass. Whatever we start with, we have to end with. So, when a chemical reaction occurs, what we're talking about today, bonds are broken and new bonds are formed. So we take some certain chemicals, we break the bonds that they might already have, and we form new bonds, and therefore it's forming new chemicals. Typically, energy is either produced, and we would call that exothermic, or energy is absorbed, and remember we call that endothermic. New compounds are formed or decomposed into their new elements. I already talked about that. You'd never end with the same compounds that you started with. And the law of conservation of mass is always obeyed, and that's where balancing comes into play. So, first off, some vocabulary, reactants and products. Reactants are what you start with, so the things in red here are the reactants. And again, those are the things that undergo some sort of change. Maybe they're forming new bonds, maybe they're breaking old bonds. But they undergo some sort of change and they turn into new chemicals, and we call those new chemicals products. And so that's what we have over here in purple. The symbols that you might see, typically you're just going to see a single arrow. We call it the yield sign. It means that the stuff on this side, on the reactant side, is turning into this stuff on the product side. So when we're actually reading a reaction, we might say yields, or we might say produces, or reacts to produce, anything along those lines. Now, we use a single arrow when a reaction goes to product and then it stops. So when something burns, you start with, let's say, a chunk of coal, carbon, and it burns and it turns into the products and then it's done. Other reactions, you might have reactants turning into products, but then some of the products actually turn back into reactants. So the reaction is actually going in both directions, and so we do a double-sided arrow. And we call these reversible reactions because they never really go to completion. They never produce 100% product. In the end, you actually have a mixture of reactants and products, and we talk about those later in the year when we talk about equilibrium. Other symbols that you'll see: solid, gas, liquid, and aqueous. And these just tell us what state the substance is in, because if you think about it, anything can exist in the solid, liquid, or gas state. And so we need to specify which one it's in. Some substances can also be dissolved in water. And so if it's dissolved in water, it's not really a solid, gas, or liquid, it's a mixture. And so we need something different to show that. And so we put AQ to mean an aqueous or water solution. So the key difference that I want to point out is between these two right here. They're both sodium chloride. They're both NaCl. That's not different. What's different is that this is the solid ionic substance, sodium chloride. So this would be actual salt crystals that you shake out of your salt shaker, whereas NaCl aqueous would be salt dissolved in water, so what you might gargle when you have a sore throat. So the states listed at the end of it are just telling us what state they're in. Another one that might easily exist in many different forms is H2O. So H2O with a liquid would of course be liquid water in your cup. H2O as a solid would be the ice cubes in your cup, and H2O as a gas is the humidity that we feel in the hot, hot summer. All right, two more symbols. If you have a triangle above the arrow, it's simply indicating that the reaction was heated and that helped the reaction to occur. Sometimes reactions don't happen on their own at room temperature, but if you apply heat to them, it'll speed up the process. And so if that happens, we just write the triangle to indicate that heat was added. Some reactions happen very slowly, but they can be sped up with a catalyst. So MnO2 is a catalyst for the decomposition of certain substances. So the substance would decompose on its own, but a catalyst is simply a chemical that speeds up the reaction. Okay, so when we have a catalyst present, it's not really a reactant. It's not really a product. It's just a helper. It speeds up the reaction. And so we don't write it on the reactant side. We don't write it on the product side. We write it above the arrow. And again, MnO2 is just one example of a catalyst. Several different chemicals could be catalysts to all sorts of different reactions. If the catalyst was potassium iodide, we would write potassium iodide above the arrow. There's a certain reaction where a slice of potato can act like a catalyst, and so we could write potato above the arrow. It's whatever that particular catalyst was. All right, so what we're going to talk about now is a chemical equation and how do we actually read it out loud using those symbols. So we just kind of take it piece by piece. So the first thing that we encounter is this substance right here. It's NaCl, which is sodium chloride, and this AQ tells us that it is a water solution. So we would say a water solution of sodium chloride. The plus sign over here means that it reacts with, because both of these two things are reactants. And so we would say a water solution of sodium chloride reacts with a water solution of silver nitrate. So those are my two reactants. The arrow, again, you could say yield, you could say reacts to produce, whatever you choose to say. I'm going to say reacts to produce, and then we would list our products. So again, you name them and you might say the state of it. So reacts to produce an aqueous solution of sodium nitrate and a solid silver chloride. Okay, if we wanted to get really specific, technically, because we're mixing two aqueous solutions together and we're creating a solid, we could say that the silver chloride was a precipitate. PPT is the abbreviation for that. So if we were to practice this one, we would say solid iron 2 oxide reacts with solid carbon under heat to produce solid iron and carbon monoxide gas. All right, so we're going to take a moment and I want you to pause the video and I want you to put this into words, write it down, and we'll go over the answer in a second. So pause the video. All right, so you should have had a chance to write the word equation. So you should have written something like solid calcium hydroxide yields solid calcium oxide and liquid water. Again, the yield, you could say a variety of things, reacts to produce, but make sure that you got the names of these substances exactly correct. Calcium hydroxide, calcium oxide product, and water. That one's pretty easy. All right. So what do we mean by balancing them? This is our main goal for today. Balancing an equation is necessary so that we have the correct amount of reactants and products, and essentially it's going to satisfy the law of conservation of mass and make sure that whatever we started with, every single atom is accounted for on the product side. The way that we do that is by using coefficients. And just like in math, a coefficient is a number out front. In math, you might see it as 2x. The 2 is the coefficient. In chemistry, in this chemical equation here, we have a coefficient here as 2. Okay. We also have some understood coefficients. Where there's no coefficient listed, it's really an understood 1. And what these represent, you could think of them as atoms, and that's what we're going to use mostly today. If it's a molecule, like HCl, it's a molecule, we would say that's 2 molecules of HCl. If it's ionic, we would say formula unit. So the magnesium chloride, we would say 1 formula unit of magnesium chloride. In the next unit, we're going to actually refer to the coefficients as representing moles of those substances, but we'll get there later, okay? All right, so how do we actually go about balancing a chemical reaction? There's a series of steps. First off, if you're given a word equation, you have to write the equation with the correct formulas and symbols. If you don't use the correct formula, you're going to have a really hard time balancing. So if it says calcium chloride and you write that, you're going to have a really hard time balancing it because that's not the formula of calcium chloride. You have to remember to do the crisscross rules that we learned earlier. So, sorry, that should be a minus 1. Minus 1. So when you crisscross that, you actually get CaCl2. So you have to write the correct formula. So you have to remember our nomenclature from the last unit. Next, you have to remember when you're writing the correct formulas that some elements are diatomic. So these, we've already talked about them this year. I call them Hernoffelbreis. Sometimes they're called Brinkelhoffs. H-chlorophen. There's all sorts of things that can help you remember which elements that they are, but it's essentially 7 elements. These always exist as pairs unless otherwise stated. So if I simply say that you have fluorine gas, you have to write F2. Now if something's not on this list, say phosphorus, you would just write the element symbol, or sodium, you would just write the element symbol. But if it's one of these 7, you have to include the little 2 down there. And again, if you don't, you're going to have trouble balancing it, and you're not really representing what the chemical is. All right, so once you have it all written correctly, you can actually start the balancing process. You essentially add coefficients to the formulas to make the number of atoms of each element on both sides the same. And remember, the coefficient is a whole number before a chemical formula. You can't put a coefficient in the middle of a formula, and I'll give you a bad example of that later. So you might want to write this down. This is not set in stone. This is just a suggestion. If you're looking at an equation and you're trying to balance it, this is how I typically go about it. I try to balance the metals first. After that, I try to balance any polyatomic ion that shows up on both sides of the arrow. So if you have something phosphate on one side of the arrow on the reactants and something phosphate on the other side, essentially you can balance the polyatomic ion phosphate as one single unit. If you have phosphate on one side, PO4, and just plain phosphorus on the other, you have to consider the phosphorus and the oxygen separately. Save your nonmetals for after the polyatomic ions, and then generally always save oxygen and hydrogen for last. Sometimes oxygen and hydrogen show up more than once on one side of the arrow, and so they can be difficult to interpret at the beginning of the problem. And if you have some other coefficients filled in already, it sometimes helps to save those until the end, and then they're easy to figure out. All right, so now we're going to talk about the things that you are not allowed to do when you're balancing a chemical equation. The first thing you can't do is add a coefficient in the middle of a formula. So if you have NaCl and you decide that you need 2 chlorines, you cannot squeeze a 2 right in there. So you're not allowed to do that. They can only go up front. That's essentially changing what the chemical is. It's not NaCl anymore, so you can't do that. And you can't change the subscript of a correctly written formula. So again, if you have NaCl and you decide you want 2 chlorines, you cannot do that because there is no such thing as NaCl2. That's not sodium chloride anymore. So if you're in that situation and you have NaCl and you decide that you need 2 chlorines, you have to put the 2 out front. Now, does that also change your sodium? Yes, you have 2 sodiums and 2 chlorines, and that's something that you're going to have to figure out as well. How do you deal with the 2 sodiums? But that's your only choice. If you need 2 chlorines, you have to put the 2 way out front of the chemical formula. Okay, other than that, pretty much practice makes perfect. Balancing chemical equations can sometimes get tricky. Some of them are very easy, some of them do get complicated. So, my best advice is if you're trying to balance a chemical equation, erase your coefficients and start over. Just start from scratch. Another suggestion is if you still can't get it, to double check that you've actually written your formulas correctly. Because again, if you're trying to balance a chemical equation and you have calcium chloride written as CaCl, you're going to encounter problems because you don't have the formula written correctly. So practice makes perfect. You'll get there. So let's do some examples together. So on this one, I'm going to show you kind of a long, drawn-out way to solve this problem, and then we're going to kind of do a more streamlined approach later. But what some people like to do is actually list out all the different substances that you have, all the different elements or polyatomic ions that you have. So starting from the beginning, I see that I have potassium, phosphate, hydrogen, and chlorine. And I'm going to consider phosphate PO4 as a unit because it shows up as a reactant and a product. Okay, so I'm going to consider them and list them together. So I'm going to make a list of the things that I have. So potassium, phosphate, hydrogen, and chlorine. Okay, and now I'm going to take an inventory of what I actually have. So on the reactant side, I have 3 potassiums, so I'm going to put a 3 over here. On the product side, I only have 1. So I see that potassium is something I'm going to have to deal with. Phosphate, I have 1 phosphate and 1 phosphate. So 1 and 1. Hydrogen, I have 1 on this side, but I have 3 over here. So that's another one I'm going to need to deal with. Chlorine is already balanced, 1 and 1. Okay, so my things that are unbalanced are potassium and hydrogen. And you can balance them in any order that you want. I just prefer to do metals first, so I'm going to deal with the potassium first. So I have 3 potassiums to begin with, and I only have 1 on the product side. So I need 3 over here in the KCl. So my only choice is to put a 3 out front. Now what that does, I don't have 1 potassium anymore. Now I have 3, and that's what I wanted. But I have 1 potassium. I also have, 3 potassiums. I also have 3 chlorines. So I have to update my little inventory. I now have 3 chlorines. So we just have to keep that in mind. So now I ask myself again, what's not balanced and what should I deal with next? Hydrogen is not balanced. I like to save that till the end. Chlorine is not balanced. So let's deal with the chlorine. My chlorine, I have 3 on the product side, but only 1 on the reactant side. So I'm going to go to my chlorine on the reactant side, and I need to make it 3. So I put a 3 in front of the HCl. Now, what has that affected? Hydrogen and chlorine. So my chlorine over here is now a 3. My hydrogen over here is also now a 3. Well, look at that. Everything is balanced. My potassium I took care of earlier. My phosphate never changed. It was already balanced. The hydrogen, I said save it till the end. Well, it actually balanced itself in the process, 3 and 3. And chlorine is 3 and 3. So this is my final answer, the balanced chemical equation. And you do not have to write the 1s in as your other coefficients right there, but you can if you want to. It's just extra work. So that's kind of the long drawn out way to do it, taking inventory. And if you struggle with balancing equations, I highly recommend doing this inventory method, but we're not going to do it every time. So we're going to try to do this one faster. So rather than actually writing down the inventory, we're just going to kind of talk about it out loud. So first off, I see potassium. I have 1 and 1. That's fine. So we don't need to do anything with that. Chlorine I encounter next. Cl, Cl. 1 and 1. Don't need to do anything there. Now oxygen, I have 3 and 2. So I need to do something to help balance that oxygen. And this is actually a fairly common situation where you have 3 on one side and 2 on the other. And there's no way that you can put 1 coefficient in here and have it be a balanced equation. There's no way, because you can't put in fractions. I can't put in like a 1.5 right here. For the oxygen. Would that balance it? Yes, but we're not allowed to use fractions like that. So when we have this 3-2 situation, I like to call it the 3-2 switcheroo. So I take my 3 from one side and I put it over as a coefficient on the other side. That's nothing there. And I take my 2 from this side on the products and I put it over on the reactant side. So my 3-2 switcheroo, essentially what that does is it makes it to where I have 6 oxygens over here and 6 oxygens over here. So that has now balanced my oxygen. So my oxygen is good. Now you have to pay attention. Again, keep track of your inventory. I now have 2 potassiums and 2 chlorines. So I need to take that account on the other side. So I put a 2 right there. So my balanced equation is 2 potassium chlorates produces 2 potassium chlorides and 3 oxygens. All right, so here's another opportunity for you to pause the video and practice on your own. So pause it, try to fill in your coefficients, and get a balanced equation. All right, so I'm going to go through the process of balancing these. You should already have them done, and so this is just a quick time to verify your answers. On the first one, hydrogen's good, but oxygen needs to be balanced, so I need to put a 2 right there. And now I have 4 oxygen, so to take care of that, I need to put a 2 right there. And so that's the correct answer for the first one. Our next one, we have aluminum and oxygen. I like to save oxygen till the end, so I work with aluminum first. I see that I have 2 on my product side, so I want 2 on my reactant side. And then I look at oxygen, and there's my 3-2 split. So I do the 3-2 switcheroo. So if it had the 2 in front of it, or a 2 already, you put the 3 out front. And I put a 2 in front of the Al2O3 so that both sides now have 6 oxygens. Now you have to keep track of your inventory. Now we have 4 aluminums on the product side, so I need to update this 2 right here, and actually I'm going to erase it. This is why we use pencil in chemistry. And we're going to put a 4 right there. So this one is now complete. Moving on to the third one. I see that iron is already balanced. Sulfur is already balanced. So it's really my hydrogen and chlorine that are not. Hydrogen has 1 right here and 2 over here. Chlorine's in the same situation. I have 1 right here and 2 right here. So all I need to do on this one is put a 2 in front of the HCl, hydrochloric acid, and that's balanced. Okay? So one more to balance. The zinc hydroxide and phosphoric acid. Now on this one, the zinc, obviously you can balance as one thing. The hydroxide, I can't balance as a unit because there's no hydroxide on the product side. So the zinc hydroxide, the hydroxide, I need to consider separately as oxygen and hydrogen. The phosphate I see shows up on both sides, PO4, PO4, so I can balance the phosphate as a single unit. And then the hydrogen, here's what I was talking about earlier. Sometimes oxygen and hydrogen just show up twice on one side of the arrow. So that's why it's best to save those till the end, because sometimes they'll just balance themselves, or if you save it till the end, it's easier. So I like to start with my metals. So the only metal I have here is zinc. I have 3 on the product side, so I need to put a 3 in front of the zinc right here. Next, I like to balance my polyatomics. For my phosphate, I have 2 on the product side. So I want 2 on the reactant side, so I put a 2 in front of the phosphoric acid. Next, I need to deal with my oxygen and hydrogen. So it's my standalone oxygen, not the oxygen in the phosphate, my standalone oxygen and hydrogen. So I'm going to think real quickly about what I have. In the zinc hydroxide here, in this chemical, the oxygen has a 2 subscript, but there's 3 of them. So I really have 6 oxygens over here. So I need 6 oxygens in the water over here. So I'm going to put a 6 out front. Okay, I'm going to erase some of my little scratch work. Now I need to analyze the hydrogen. Well, how many hydrogens are right here? That's 6. But again, I have hydrogen over here too. You have to pay attention to everywhere where you find it. So I have 2 hydrogens because of the subscript, but there's 3 groups of 2, so that is also 6. So my hydrogen on this side is really 6 plus 6, so that's 12. So good thing I have 12 hydrogens over here. So moving on, what we're going to practice now is going from words to a balanced equation. Okay, so the most important step here is the first one, that you actually write the equations correctly and then balance it. So carbonic acid, we need to think about the acid rules. An ic ending indicates that it was an 8 ion. So we're going to have hydrogen paired up with carbonate. So that's H2CO3. Decomposes into. That indicates that that's the end of my reactants and I have my arrow. So decomposes into, and it produces carbon dioxide and water. So those are fairly easy to write. We're familiar with those chemicals, carbon dioxide and water. And so the first thing we had to do was just write out the chemicals. And now it's not necessarily a balanced equation. We have to check. So this one has 2 hydrogens and 2 hydrogens, 1 carbon and 1 carbon, 3 oxygens, and we have 3 oxygens over here because that's 1, 2, and 3. So this already is a balanced equation, which is nice. All right, so number 6, barium chloride reacts with phosphoric acid to produce barium phosphate and hydrochloric acid. So we have a lot of formulas to write here, so it's important to just take it one step at a time. So barium chloride is ionic, so we have to think about the crisscross rule. So that's BaCl2. Reacts with, so that's indicating there's 2 reactants, so I need a plus sign. Phosphoric acid. Again, an ic ending on an acid name indicates that it's from the 8 ion, so phosphate. The acid is going to be H3PO4. That's PO4 is phosphate. All right, moving on. To produce indicates the arrow. Barium phosphate. Again, barium phosphate is going to be ionic, so we think about the crisscross rule. Ba3 PO4. We need 2 phosphates, so we need to put it in parentheses. And indicates our plus sign, hydrochloric acid. Hydroic on the acid indicates that it was the ide ion. So this is just hydrogen chloride, HCl. So we have all of our formulas written correctly, and now we need to balance it. So start with your metal, barium. So barium has 3 on the product side. I need 3 on the reactant side. Next, polyatomic ions. So I have phosphate on both sides of the arrow, so I can think about phosphate as a whole thing. So PO4 is, we have 2 on the product side, so we want 2 on the reactant side right there. Now I consider non-metals other than hydrogen, oxygen, leave those for the last. So chlorine. Chlorine has a coefficient of 3 and a subscript of 2, so you multiply them. I have 6 chlorines on the reactant side, so I need 6 chlorines on the product side. And now hydrogen last. I have 6 hydrogens in the HCl, and look at this. I have 6 hydrogens on the reactant side because it has a coefficient of 2 and a subscript of 3, so you multiply them. So this has turned into a balanced equation. All right, so a couple more practice ones. Calcium reacts with water, so let's write those out. Calcium is just Ca, reacts with water, H2O, to yield, there's your arrow, an aqueous solution of calcium hydroxide, so that's CaOH2, it's ionic. Now it says it's an aqueous solution, so we can throw in that information and put the AQ. You don't need to, but it's useful later on. And hydrogen gas, so that's plus H2, because H2 is one of our diatomic elements. Calcium was not, so I did not put Ca2. Calcium is just a plain element, Ca. All right, so now I start my balancing process. I start by looking at calcium, and I see that calcium is already balanced. So we can move on to either oxygen or hydrogen. Let's look at oxygen. I have 1 to begin with, and I have 2 on the product side because I have 2 hydroxides, so that's 2 oxygens in there. So I need to put a 2 in front of the H2O. So that's balanced. And now I look at the hydrogen. Hydrogen here has a, on the reactant side, has a coefficient of 2 and a subscript of 2. So I have 4 hydrogens there. So I need 4 hydrogens on the product side. Well, if you're not careful, you might think you need to put a 2 right there. But if you are careful, you'll notice that we have 2 hydrogens in the hydrogen gas. We also already have 2 hydrogens in the hydroxide, so that actually adds up to 4. So my final answer is done. All I needed to do was put the 2 in front of the H2O. All right, for number 8, we again need to start out by writing the balanced equation. So, mercuric sulfide. Ic, as the end of a Latin name, indicates the higher possible charge. So this is mercury plus 2. So that's HgS when we do the crisscross. And calcium oxide is CaO. Yields, mercury is just Hg plus calcium sulfide, Cas, and calcium sulfate, CaSO4. So this one has a lot of things going on. We have sulfur showing up in 2 places on the product side. We have calcium showing up in 2 places. We're going to have to be very careful. So to start out, the only element that's not balanced is oxygen. So I have 4 on the product side. I need to put 4 in front of the oxygen on the reactant side, and it only shows up in 1 place. Now I have 4 calciums. So I need 4 calciums on the other side. Calcium shows up in 2 places, right here and right here. I really don't want to mess with this one in the calcium sulfate because that would also, again, mess up my oxygen. So what do I need to put here? How many calciums do I need here to add with this one to equal the 4 on the other side? So I need to put a 3 right here in front of the calcium sulfide. Okay. Now, what does that disrupt? The sulfur. So the sulfur, again, you need to be very careful here because the sulfur shows up in 2 places. I have 3 sulfurs right here, but I also have 1 over here. So I have a total of 4. So I need to put a 4 in front of the mercuric sulfide And now what does that mess up? My mercury. So now I have 4 mercuries. I need 4 mercuries. Okay, so that is what was necessary to balance this chemical equation. This one was tough because we had a lot of elements showing up twice. And you have to be very careful when you have elements showing up twice. All right, let's do a few more. Sodium plus chlorine yields sodium chloride. So this is actually a fairly explosive reaction because sodium and chlorine react very violently. Sodium is Na, and chlorine is Cl2. You have to remember that chlorine is one of the diatomics. Yields means our arrow sign. Sodium chloride is just NaCl. Now, what a lot of students are tempted to do when they have a situation like this, sodium and chlorine, they just want to get rid of this plus sign, smush them together, and write NaCl2 and call it a day. And it doesn't quite work because, again, we talked about it. NaCl is the formula of sodium chloride. There's no such thing as NaCl2. So to balance it, you have to use coefficients. So we put a 2 in front of the NaCl, and therefore a 2 in front of the Na. That one's fairly easy. All right, we have one more. Rubidium chlorate. Okay, so rubidium is in group 1. We don't see it often, but it's Rb plus 1. Chlorate is ClO3 minus. So that's going to be RbClO3. Decomposes. Generally, when you see the word decomposes, it means you only had one reactant, but the word decomposes translates into the arrow. So it produces rubidium chloride. Again, that's a 1-to-1 ratio, so it's just RbCl and oxygen gas, which is O2. So the rubidium is already balanced 1-to-1. The chlorine is already balanced 1-to-1. Oxygen has the 3-2 split, so we do the 3-2 switcheroo. So I take the 3 from over here, put it right here on the product side. I take the subscript of 2 on the product side and make it the coefficient on the reactant side. Again, the reason that works is because if you have 3 and 2, essentially you need to get them both to 6. So you multiply the 3 by 2, you multiply the 2 by 3. And of course that means now I need 2 rubidiums and 2 chlorines, so I need to put a 2 right there. So now this is a balanced equation. All right, the last suggestion I have is an example that I don't have here in the notes, but I just want to show you. Let me go to a blank screen. Let's go to a white screen. Okay, sometimes you're going to see reactions where you have maybe C3H7. These are called hydrocarbon compounds because those are the 2 elements they have, hydrogen and carbon, reacting with oxygen to produce carbon dioxide and water. So when you go about trying to balance these to begin with, the carbon first, we have 3, so we would put a 3 right here. Now, the hydrogen we can try to deal with. I have 7. Well, what can I put in front of that to make it 7? Technically, I would need to put a 3.5, but I can't use fractions, okay? So, because it's 3.5, if I multiplied that by a whole number, if I multiplied it by 2, I would get a whole number. So I'm going to kind of start from scratch. I'm going to get rid of the coefficients I'd already written. And I'm going to put a 2 in front of the hydrocarbon and try again. Okay, so if you get to that point where you're stuck and you think you need to use a fraction, you can figure out what do I need to multiply that fraction by 2 and put that out in front of the hydrocarbon. So now we start from scratch. Now I have 6 carbons, so I put 6 in front of the carbon dioxide. Now I have 7 times 2 hydrogens, so that's 14 hydrogens. So I need to put a 7 in front of the water to make that into 14 hydrogens. All right, so finally I need to look at my oxygen. And my oxygen shows up in 2 places on the product side. I have 6 times 2 in my carbon dioxide, so that's 12, plus 7 on the water. So that equals, 19. Again, 19. What can I put in front of O2 to make it a 19? It would have to be a fraction, okay? It would have to be 9.5. And again, I can't do that. So I'm going to have to try again, multiplying my coefficient out front by 2 again. So I'm going to erase some of the scratch work I've done. I'm going to erase the coefficients I already put in. Again, pencils are useful. And instead of a 2 out here, I'm going to multiply it by 2 again. I'm going to try a 4. Let's see what happens with a 4. Okay, so now with a 4, I have 12 carbons. 4 times 3 is 12 carbons. So I'm going to put a 12 right here. I have 7 times 4 hydrogens, so that's 28 hydrogens. It's a 28, not something else. So that means I need to put a 14 right here. Numbers are getting big. It's okay. It happens in these hydrocarbon compound reactions. So now my oxygens, I have 12 times 2, so that's 24, plus this is 14 oxygens. So I have 38 oxygens. So I need 38 oxygens right here. Well, what can I put out front to multiply by 2 to give me 38? 19. Whew, so that is a big problem. Sometimes these are called combustion reactions when you have a hydrocarbon reacting with oxygen. Sometimes these combustion reactions can be tricky to balance. If you get stuck, the main idea is stop and change your number in the very, very beginning. And sometimes that helps you balance it. Sometimes using a 2 or a 4 could be very useful. Sometimes a 3 works. So it's kind of just trial and error, and you can figure out what it is you need to do. So I hope that's helpful. I hope that you have a better understanding now of how to write and balance a chemical equation. Thanks for watching.